Hello everyone, my name is Peter and today we're going to talk about Softmax activation. We're going to look at this problem on mlpro.io, a website where you can test your understanding of these fundamental machine learning concepts by coding them up and testing them out. So today, again, we're talking about softmax activation, which is a critical concept in classification where you're trying to predict between multiple categories. So now, softmax is usually applied at the end of a machine learning model. So when I say the end of a machine learning model, let's take a look at one. And let's take a look at a multi-layer perceptron, which is a type of neural network. And so you could apply softmax activation to the final set of nodes. And you normally want to do this when you're classifying between more than two objects, but you could also make it work with two. And so going back to the softmax activation page, let's take a look at what the formula is doing. So given an input number from a probability distribution, or not, just any general input number, you want to take e to the power of that number and divide that by the sum of e to the power of every number. So for example, let's take a look at the code segment. If we had the number 3 that was the output of one node in a neural network, the number 4, which was the output of another node in the neural network, and finally 5, which is the output of maybe the third node in a neural network, then the softmax activation for this 3 is going to be e to the third power divided by the sum of e to the third power plus e to the fourth power plus e to the fifth power. And this denominator is also going to be used to calculate the softmax activation for this number, which is going to be e to the fourth power divided by that sum for the denominator. And same thing here. So let's think about why this is done. What is the effect of this? Well, let's just focus on the numerator for now. So the numerator, we're taking whatever number we get, and we're saying take e to the power of that number. Well, what's that gonna do? Let's just think, well, e to the third power, that's gonna raise the number to be pretty large. What about e to the fourth power? That's gonna be even larger. And even though it's one number greater than 3, it's e times, or 2 point something times larger than the previous number. What about the last number, 5? Well, that's going to be e squared times larger than this fourth number, even though it's only 2 values larger. It's only the difference between this number is just 2, and yet its softmax activation is going to be 2 times 2 point something times 2 point something, so either 4 point something or 5 point something times larger, even though it's less than twice as large as this number. So why do we do that? Well, the point of doing softmax activation is so that we get probability outputs of each number. And we want those probability outputs to be very large for whatever class it's most confident about. So if 5 is the largest output node value, then we want that probability to be by far way larger than the other numbers. We want the rest of the numbers for their probabilities, the closer they are to 5, the higher their probability is, but if it's way lower, then it's basically a 0 probability. So that's the numerator. What about the denominator? Why are we dividing it by the sum of all the e to the x's? Well, the reason is that we want a probability distribution. And so if we just sum up all the numbers in our softmax activation, then we could divide by that, and then all of these numbers will sum up to 1. So like when we have a probability distribution, we want it to be like 0.2, 0.4, comma 0.4, something like that, where the probabilities individually add up to 1. So just by dividing by the sum, we're ensuring that all the numbers in the output nodes will sum up to 1. And again, so denominator is creating the probability distribution, raising the numbers to e to the xi power is creating way larger probabilities for increasingly larger output values of the neural network or any multi-class classification model that you use. So last thing is, let's just quickly code this up. So we have this input function, softmax of x, and we want to calculate the softmax probability vector and return it as a NumPy array. So let's just start off with a list of the distribution that we'll fill in, and now let's loop through x. So for a in x, we want to raise e to that power, so math, import math, and let's first just calculate the denominator. So denominator is equal to the sum of math dot exponent, so this is e to the a of I power for a in x. So we're creating first a list that's just going to take every number in x and raise e to that power. I don't need a to the I, just a. So math.x of a for a in x. And then we call the sum function on this list to get the sum of everything in the list. That's our denominator. So now to fill in the distribution, we can just add to our distribution. What do we want to add to it? We want to add to it the value of the current number raised to the e raised to the current number power, and divide that by the denominator, which I might have spelled incorrectly, but that's okay. So last thing is we want to return a NumPy array of our distribution list. So let's just return that and hit the run button. And yay, we did it right. So if you want practice like this to really test your understanding of machine learning math concepts, head on over to mlpro.io and take a look at all of the problems that are listed. Sign up for the problem of the day to get an email notification for new problems. And before you know it, you will be an ML Pro.